Okay. Today I'm starting on a fresh subject. I like to call this, well, I think the fourth part of my talk. That doesn't matter. A closer encounter. Encounter with the circle. So I shall be talking about the circle, and at the center of my treatment will stand the curious concept of power of a point with respect to a circle. It is a quaint object, it's a strange object, and it is one of those circumstances in mathematics where an intuitively very appealing object, once introduced, it can start working without even looking at its finer properties. So observe me introduce the concept, and alone the presence of the concept will allow us to look at some very important problems to obtain some very interesting results. Okay, so the power of a point with respect to a circle. Let's start with a circle gamma, let's say. Okay, and well, I mean, you can imagine it's got a center at some O, and its radius is R, perhaps. Okay, and a point. Well, for purpose of illustration, I choose it a point outside the circle. Not that it will matter. Let me start with the following observation. If you take a line through P, let's say K, line K, which intersects your circle in points A and B. Let me start with the observation that the product PA times PB as signed quantity is independent of the choice of the point K, choice of the line K. So let me, so it means if I take another point, another line through P, let's say K prime, if it intersects my circle in A prime, B prime, then I claim that, so let's say observe that the quantity PA times PB is exactly the same as PA prime, PB prime. Now, why is that? Well, this is a signed quantity. Let me repeat that. This is a number that can be positive or negative. So for those of you familiar with analytic geometry, you might like to understand this as really the vector product of these two vectors, okay? Or if you are not familiar, you can say that if PA and PB are in the same direction, let this be positive. If PA and PB are in the opposite directions, it's negative, so it will be. So as a directed quantity, so it can be negative or positive. So this is, okay, so these two things. Now, why is that? Well, let's look at the situation where P is outside. So since P is outside the circle, PA times PB is a positive quantity, and you only have to simply observe that. You have to simply observe that. So why is that? Well, all we have to observe is the following. Look at the triangle. P A prime B. And look at the triangle P A B prime. Well, they have a common angle. beside these two angles are equal. So you've got simply the fact that the PAB prime is similar to the triangle PA prime. Well, this similarity, of course, entails the fact that the ratio of PA, so PA, the length PA, the ratio of the length PA to PB prime is equal to the ratio of PA prime PB. Well, from this, you can get this inequality with, of course, lengths instead of directed lengths. But since this is positive, when P is outside, there is no problem. If P is inside, well, you will make the necessary changes, and you will get exactly the same thing. So, okay, so that's why. So we make the following thing. We make the following definition. Given a circle. Okay, so let me do it like this. Gamma and the point P, the power, okay, here's the concept, the power of P, the power of the point P, with respect to gamma is PA times PB, where AB are the points in which a line K through P intersects gamma. Okay. Now, of course, we have seen that. So we have seen here that. So indeed, this quantity is independent. Independent of the choice of K. Okay, so we have seen that choice of K. Okay, so that's the remark. Right, there it is. So that is the concept there. By the way, I mean, for those of you who are interested in the history of the subject, the history of what I'm going to talk about today, mainly, principally this concept of power, is very complicated. Nobody really knows who actually invented this thing. The concept of power or related ideas were in the air for a long time, beginning of the 19th century, and at the end of the 19th century, there definitely was a well-established concept of power of a point with respect to a circle, and of course the related issues. Right. So that is the thing. And I would like to make a few remarks. First of all, notice that if you choose your point outside the circle, then of course, okay, so that's your circle gamma. Then that this power is in this case strictly positive. If you choose your P inside your circle, then of course the power, which is PA times PB, is of course strictly negative. And of course, if you choose your point exactly on the circle, then quite clearly PA for instance is 0. And so for instance, the point A and P coincide, and this is the point B. So this is, power is in this case is exactly 0. So that's the first thing that you should notice, so in a sense, power is a measure of the distance of a point from the circle. In a sense, approximately. So, well, this is not quite true actually, but you can say that the power of a point with respect to a circle is somehow an indicator of the distance at which the point is. The distance between the point and the circle in a sense. Okay, so let me make this absolutely clear. So we have, okay, so let me make also the following remark, finally. For instance, you have got this point, okay, so okay, here's your circle, and here's your point, and you can, well, let me take the situation where the point P is outside the circle now. So you can draw any straight line, okay, and you can take the product of PA, PB. It really doesn't matter where you choose it, A prime, B prime, so on and so forth. You can do it like this, A double prime, B double prime. Now, let me take this straight line. So I've chosen K, for instance, K prime, K double prime. Let me take the limiting situation where I look at not at any straight line through P, but let me look at the straight line, one of the straight lines which are tangent. Okay, which are tangent. So let's say it touches the circle in T. Well, in that case, we have got a rather remarkable situation at hand, because you see, in that case, this PA and the points A and B collapse into T, and that's the center. And if you join O and T, this is a right triangle. So in fact, in this case, this shows us that the power of the point P is in fact the square of the tangent. So this is PT squared. Okay, so if P is outside gamma, then it's this. And even more remarkable. So if you designate the distance between the point P and the center O with D, then the radius of the circle as R, then the theorem of Pythagoras tells us quite simply that this power is given by a very simple formula, which is D squared minus R squared. Okay, so that is a rather important formula. That's a rather important formula, and in fact, I shall immediately make use of it. To derive a rather interesting result. Okay, so that's power of a point with respect to a circle. Now, this formula is, I think, rather descriptive. So, I mean, this formula reveals the power as well. I mean, in a sense, it is the distance of the point P from the center of the circle. Yet it is in a sense tempered. It's changed a little bit depending on the size of the circle. Okay, so I mean, if the size of the circle is small, the power is rather like the square of the distance between the point and the center, so on and so forth. So this is, as I said, it's an indicator of the distance of the point from a circle, and taken into account also the size of the circle. So it's a curious thing, anyway. And in my opinion, I mean, of course, you will experiment with the thing yourself, and you will obtain your own impressions. But I think the really crux of the matter lies in the fact that the product PA times PP is quite independent of the choice of the line K through the point P. That's the crux of the matter, in my opinion. Why the thing is so important and useful. So why is it so important and useful? Let me give you an application. And in fact, okay, so let me call this application number 1. How you can use the concept of power. So there will be many problems and exercises to show you how we can make use of this concept. But so let me give you 1 or 2 striking examples. The example which I would like to bring to your attention is about the triangle. It's a very famous formula. It's called the Euler formula. Well, I think there are hundreds of Euler formulas. So, you know, Euler is a real painful thing for the mathematician. I mean, whichever part of mathematics you look at, he is there. And he has already done the most important thing, the Euler formula in the triangle. It is the following, the Euler formula. It simply says that if you take the distance between, in a triangle, the circumcenter and the incenter, if you take the distance between them, the square of this distance is in fact r squared, the circumradius squared, minus 2rr. Now this is possibly one of the most beautiful formulae in all mathematics, and of course it can be proven in many different ways. Euler proved it, I think, in a rather cumbersome fashion, and I shall give you a proof which, in my opinion, is quite straightforward and relies on the concept of power. Okay, here it is. So let me start. Let me start with the circumcircle. Okay, and I'm sorry about these stupid circles. You know, that's. I think I shall get myself some kind of compass. Anyhow, okay. So here is the triangle. Okay. Right. Okay. So let's construct the incenter. Well, A, B, C. Well, this is the circumcenter. That's rather easy. So let's call this O. And yeah, okay. Now, well, let me take the midpoint of BC, the arc BC, and let me join it to A to obtain, of course, the internal angle bisector. Okay, so these two angles are equal. Okay, so you can also take the you can also do something similar with B, and that will get you more or less this. Okay, so this is now that's getting difficult. Okay, so this is your point I. So this is the point I. the incenter. Okay, so these two angles are equal. Okay, here we are. Okay, so what we want is this length OI. Okay, so let me call this D if you wish. Okay, and right, there we are. And if you like, let me complete this picture by dropping a perpendicular from I onto the side AB and noticing that, of course, this length is R. Okay, so let me call this, I don't know, you can call this anything. Let me call this point U. It's in fact the point in which the in circle touches the side AB, so I think it's natural to call it U. There we are. Okay, let me start observing one thing. So let's call this half angle 1. So this is 1. So let me call this half angle 2. So this is 2. So you notice that this angle here being the external. Okay, so this is my, of course, my incenter, right? Okay, so this angle here being the external angle at I in the triangle IAB, this must be 1 plus 2. Okay? So this external angle is the sum of the non-adjacent two internal angles. That's good. Also, notice that if you look at, okay, so let me call this point, I don't know, K. If you look at this angle is the angle actually subtended by the arc KC at B, but it's the same as the angle that it subtends at A, which is 1. So this is 1. So it means that this angle is 1 plus 2. So it means that the triangle KIB is isosceles. Okay, let me make it clear. The length Ki is exactly the same as the length Kb. Okay, so that's the one thing that I would like to bring to your attention. Right. Now let's look at. Okay, so I will now use the concept of power. I have deliberately chosen this length to be D so that you can put it into, so that you can, in your mind, be reminded of the formula that I wrote down over there. So, the power of, let's look at the power of, so if I write D squared minus R squared, that's the power of the point I with respect to the circumcircle, of course. With respect to the circumcircle. That's great. Okay. So, and that's D squared. That's what I'm trying to find. If you like, let me write it as OI. Okay, so that we know exactly what we are doing. Okay, the power of I with respect to this circle is, oh, I'm sorry about that. That's not small r, that's big R. Of course, yeah. The power of I with respect to the circumcircle. That's good. So, how do I compute it? Well, I know that it is IK times IA. Now, the point I, the incenter, is always inside the triangle, hence it is inside the circumcircle. So this is in fact minus the distance IK, IA. Please pay attention to the way I'm being careful about distinguishing between directed products and the lengths which are positive. So they are all very different things, and I rather expect the same meticulous attention to directed and undirected quantities, especially when you are writing your exam papers. Okay, IK times IA. Now, IK can be replaced, of course, with KB. So this is so minus instead of KB. And let's IA stand. Now, we are finished, actually. We are finished. Because you see, well, let me use a little bit of color to better indicate what is going on. Well, I've got some blue. Right, so that comes in very handy. Now, I would like you to pay attention to, now, what about this triangle? I mean, that's rather nice. So let me draw the diameter through K. Well, let's call this point L. Now, this is a right triangle. Do you see that the triangle LBK, which is a right triangle, is similar to the triangle AUI? So this tells me that, so let me write it down. LBK is similar to the triangle AUI. So it follows from this that if you take the ratio of LK to KB, that's exactly the same, LK to KB. That's exactly the same as the ratio of AI to IU. But notice, check that LK is of course twice the circumradius. That's great. IU, on the other hand, is exactly R. So this tells me that in fact KB times AI, which is this, is exactly the same as 2R times small r. So minus 2R. Finished. So I've in fact obtained, I've obtained that this object squared minus r squared is in fact minus 2r, I'm sorry, r, which is exactly this formula. Okay? So that's, I mean, of course, this problem can be handled in many different ways, but I think this is truly a very good example of a circumstance when alone the knowledge that a concept called the power of a point with respect to a circle makes sense can be used directly, and that's exactly what I have done. Okay, so that's a formula by Euler. Okay, so it's I would like to leave it to you as a good exercise. I think you will also slowly acquire an instinct for that kind of thing. It's possible to obtain a similar formula, and I think I have set it in the past as an exam question. You can do it, for instance, with the external so 10 circles, not the in circle, but the x circle. So, for instance, if IA is the center of the x circle opposite A, then you can write down a similar formula. You can actually write down r squared, and exactly the same thing, of course, and as you expect, small r will be replaced by RA, small ra, except there is one serious difference. This minus is replaced with plus. Okay, so I would like to, okay, so so I mean, of course, you may go home, and of course you will review the proof that I gave you, perhaps understand the finer points. But I think it's a very good exercise directed to go to this and try to do something to prove this formula using exactly the same ideas. with, of course, certain changes, certain twists. So this is left to the student. Left to the student. And of course, you can do it for the X circle opposite B or C, so you obtain very similar formulae like that. Okay, there it is. This is a formula by Euler, and I've just proven it in 2 lines, just making very simple observations along with just noting the power of a point with respect to a circle written in 2 different ways. So that solves my problem completely. Now that's rather remarkable, I should say. Okay, so that's, I think this is a rather good example. And of course, you should notice that I have just used the concept itself. I have not looked into the finer properties of the concept of power. That will take a little bit of time. Okay. Right. I would like to give you a second application. Let me first state the theorem. And then possibly the proof. I shall do the proof in my next lecture, next hour. This is a theorem which is, okay, so application 2. This is a theorem which is attributed usually to the great French genius Pascal, Pascal's theorem. It is, you will notice certain similarity, formal similarity with the theorem of Pappus. Let me just give you the statements, and then, as I say, the proof will follow in my next lecture. So what happens is this. You take a conic section. Okay, so of course you don't know as yet what a conic section is, but I mean, it's an ellipse or a hyperbola or a parabola or a circle. You know that. We shall in fact come back and revindicate all this. So, I mean, if you wish, let it be an ellipse, let it be a circle if you wish. And, okay, so here is a conic section. So what I'm drawing is really an ellipse. I mean, something that looks like an ellipse. It's really, okay. And you take 6 points on it, 6 distinct points. And let's say they are A, B, C, and the A prime, B prime, C prime. Now, Charita, from the way I am designating the points, you should have noticed that there is a formal resemblance between this object and the Pappus theorem. In fact, it is exactly the Pappus theorem. What you do is you join the line B prime C and BC prime and let them intersect in a point X. And you intersect CA prime and C prime A, and let them intersect in Y, and finally A prime B and AB prime intersect in Z, well, we claim that X, Y, and Z lie on a line. They are collinear. Okay, so this is Pascal's theorem. In fact, Pappus theorem, the Pappus theorem is a special case. And why and how it's a special case, I will explain in a minute. Okay, so the Pappus, so a generalization. So this is a generalization of the Pappus theorem. Pappus theorem. Okay, children, so I'm talking about conic sections, which is going to be our third, so to speak, interesting point of contact with this higher geometry, projective geometry. So I think let me stop here, and let's take a break. After the break, I shall give a proper statement. I shall give you a proof, and I shall give the proof only in the case of a circle, and I will claim that it's sufficient to prove it on a circle. Why that's the case, and that statement will be revindicated towards the end of the term in a rather big way. So it's another big deal. Okay, let's take a break.